What I have on the screen is a 20 megahertz burst, that is an AM modulated 20 megahertz, where the modulation is 100 kilohertz square wave. So what you see is the analog discovery oscilloscope to kind of give you an idea of what the waveform looks like. And at these frequencies, of course, I find it phenomenal that the analog discovery 2 can even trigger on this signal. But what I'm going to do is move this off the screen now. And here is the spectrum analyzer. I'm going to now run it to show you what the spectrum of the signal looks like, and so that you can get an idea. This is the carrier in the center here. To the right and left are the first sidebands, that is the first upper sideband and the second upper sideband. And by that, this is the entire sideband because we're looking at a square wave. So this is, for example, the fundamental frequency. This is the third harmonic, fifth harmonic, and so on of the modulating signal. The reason that I show you this is I got to working with the analog discovery 2 and the spectrum analyzer, and I realized that it has some wonderful properties, and for the money it's a real value. But the one thing that it's limited by is its 50 megahertz bandwidth. Now, actually, because the scope, which uses this input, and by the way, this is just a fast Fourier transform, it's not a true spectrum analyzer. But let me show you what a true spectrum analyzer shows for this same signal. Up here, this is the Instec GSP 730, which is a true spectrum analyzer. In other words, it's not doing a fast Fourier transform. It's actually using a swept frequency, at least a digitally swept frequency, to pick out, once again, the carrier in the center, the fundamental of the modulating frequency, in other words, the 100 kilohertz, and then the odd harmonics moving up from there. So, what I was wondering is, was there a way, an easy, economical way, to expand the frequency range of the analog discovery 2? And I think I have found a way that that can be done, that's cheap enough for a university lab, for example, to be able to afford multiple copies, and to extend the frequency range to any 50 megahertz portion of a frequency spectrum. Now, you can't get more than 50 megahertz, but let me set up what I'm testing, and you'll get an idea of what I mean by that. First, let me come back over to the analog discovery, and then instead of the end frequency being 21 megahertz, let's set it to 50 megahertz. And there you see, way on the left, this is the, this would be 10 megahertz, this would be 20 megahertz. And then I have set the stop frequency to 50 megahertz, which would be way out here. So the purpose of this is to say, well, suppose that what you want to look at, let's suppose that you're working on a 10-meter amateur radio transmitter for say packet or other data. What you're interested in is not just the fundamental and its sidebands, but you're also interested in the harmonics. Well, the problem is that on the analog discovery, since it only has a 50 megahertz bandwidth, you can look at the fundamental and its sidebands, but you can't look at the second or third harmonic of the carrier and its sidebands. And of course, those are important in complying with FCC specs and so on for transmitters. So it occurred to me that, you know, it would be a lot more useful if you could have some kind of easy way of picking a 50 megahertz segment of spectrum, or less, up to 50 megahertz, and displaying it on the analog discovery. So let me show you what my thoughts are and kind of how I would go about doing that. So here is what we're trying to do, a diagram. Suppose that we have a 28 megahertz signal, which is in the 10 meter band, and it has sidebands. And here I've only drawn a single upper and a single lower sideband, that is a single frequency like a sine wave, as the modulating frequency rather than that square wave we looked at earlier. But we'll do a square wave here in a little bit. So this is intended to show what I'm trying to accomplish. The idea is, if I mix that 28 megahertz signal with a 25 megahertz local oscillator, it will in effect move the 28 megahertz down to 3 megahertz. That is the difference between 28 and 25. 3, of course, is well within the range of the analog discovery. In fact, 28 would be as well. But now think about what would happen if we want to look at the second harmonic. The second harmonic of 28 would be 56 megahertz. If we subtract 25 megahertz from 56 megahertz, we get a difference frequency which is now well within the range of the analog discovery spectrum analyzer. So let's set this up first on a regular spectrum analyzer and then on the analog discovery too, and see what it looks like. Now we're back to the InStec analyzer, and you'll notice that the center frequency is 3 megahertz. That's here. We have the lower sideband and the upper sideband. The start frequency is 2.5 megahertz and the stop frequency is 3.5 megahertz. So how are we achieving this? Well, we're doing this with a ZP3 mini circuits mixer where the local oscillator is being supplied from the generator at 25 megahertz. The RF signal here is that 28 megahertz AM modulated signal, and the output is of course what we're observing on the spectrum analyzer. Now the ZP3, as some of you who watched the videos from a few weeks ago will remember, is a packaged frequency mixer made by Mini Circuits that works between 0.15 megahertz and 400 megahertz. It uses it's packaged in a metal package with B and C connectors. Mini Circuits makes a wide variety of frequency mixers. I'm only using this one because that's the one I have on hand. If you remember the experiments that I did with the analog discovery and the Mini Circuits mixers, this is one of the mixers that I used. So we're just using double duty here. So now let's move over and see what this looks like on the analog discovery. And here is the signal displayed on the Analog Discovery 2. What we have at the center is the 3 megahertz difference frequency, the lower and upper sideband. Right now we are spanning from 2 megahertz on the left to 4 megahertz on the right. Let's increase the upper frequency limit. So here you see increasing the frequency, the span. We were cutting off at 4 megahertz, which is around this point. Now we are going out all the way to 10 megahertz. And as you see, we see another frequency component here with a 25 megahertz local oscillator. We are essentially moving the 0 to 50 megahertz frequency range. We're moving the 25 megahertz point down to 0. That makes this 28 megahertz. This allows us to look at a frequency span between 25 megahertz and 35 megahertz. Now let's go up to a 50 megahertz span. And now you can see the real value. Notice that up here near the top, which is in the 75 megahertz range, in other words, remember, we now have a 50 megahertz span from here to here, but the base is at 25 megahertz, or a local oscillator is. And we'll look at this on a diagram in just a minute. So this is our fundamental. This is the second harmonic. This is the third harmonic that we would not have otherwise been able to see with the Analog Discovery. But by translating the frequency down, we are able to now see a much wider range. Now when I say wider, we can't see below 25 megahertz when we're using the mixer, because that's our local oscillator frequency. But now, instead of only stopping at 50 megahertz, we can see all the way up to 75. So let's look at that on a diagram in case that's not clear what we're doing. And then I'll talk about how you can extend this to a wide variety of other frequency ranges. So here's the basic idea. The Analog Discovery 2 has a fundamental range, that is for its spectrum analyzer, of 0 to 50 megahertz. Now, if you use a mixer like the ZP3 from Mini Circuits, and they have much cheaper mixers. This one costs around $50 if I remember right, but they have mixers that sell for less than $10 in a different package, that is a through-hole PCB package. But if you used a mixer to mix, for example, a 25 megahertz local oscillator, that then gives you a frequency span from 25 to 75 megahertz. If you use a 50 megahertz oscillator, you can go from 50 megahertz to 100 megahertz. So, the idea that I have is to build a circuit that will allow you to select either the straight-through frequency, in which case you're using the basic Analog Discovery 2 Spectrum Analyzer, or one that is mixed with 25 megahertz and one that is mixed with 50 megahertz. That would mean that you're extending the frequency range from 0 to 50 up to 100 megahertz. One of the reasons that I chose this is I was looking at the All Electronics catalog, and I noticed that they sell a 50 megahertz crystal oscillator, $1.25 each, or 100 for $1 each. So for $1.25 plus $10 for a mixer, now not a packaged mixer like this with all these BNC connectors, but a mixer that would fit on a printed circuit board and would cover ranges up to about 400 or so megahertz, you can translate the frequency range of the analog discovery 2 to display any 50 megahertz segment of a frequency range. Now, of course, when you start getting up into the hundreds of megahertz, you need to be very careful about layout and matching and a number of other issues. But for frequencies up to about 100 megahertz, this system should work quite well. And as I have pointed out, with a relatively cheap crystal oscillator and a flip-flop to divide this from 50 megahertz to 25 megahertz, you then could select between either a 50 megahertz signal, the divide by 2 of that is a flip-flop, dividing it down to 25 megahertz, or straight through. So I will probably put together a little prototype like this and recommend this to the university as possibly a project for some communication students to do in their labs to move the frequency range of the analog discovery up by quite a bit. Not only will it be a useful tool in the laboratory, but it also is a useful learning tool in teaching students the uses of mixers, not just to move one frequency, but to translate an entire frequency band from its fundamental down to some translated frequency range that's within the range of a test instrument like the analog discovery. So I hope that this is a useful idea. I am pretty sure that this much at least will work, probably up to around 100 megahertz, and if packaged in a fairly nice little aluminum box, I think it will be a useful tool that can be passed on from one group of students to another. So at any rate, I hope you enjoyed this, and I hope you'll look forward to some more analog discovery experiments in the future.